So let us work some problems regarding the static indeterminacy as well as the kinematic indeterminacy. Here I have listed few structural problems for which you have to determine degree of static indeterminacy as well as kinematic indeterminacy. So in this previous lecture, I gave the formula for finding the degree of static indeterminacy. Here it is total degree of static indeterminacy. I is given by formula n plus or minus 2j for trusses, plane truss. For plane truss structures, and I is equal to 3m plus or minus 3j for beams and rigid plane frames, plane frame structures. So this is the degree of static indeterminacy. Here, the degree of static indeterminacy, you can classify them into two types also. One is external indeterminacy, plus internal indeterminacy. This is total indeterminacy, total degree of static indeterminacy I. You can classify that as, or you can just treat it as equal to sum of degree of external indeterminacy as well as internal indeterminacy. Here, as per definition, I told total degree of static indeterminacy is the number of unknown internal member forces and external support reactions in the given structure which you cannot determine by equation of statics only or equations of equilibrium only. In this is the total unknown forces, member forces, external support reactions. Here also member forces, external support reactions. Here these are the equations of equilibrium available at all the joints of the structure. So total unknowns minus equations available, that is your degree of static indeterminacy. The number of unknown internal member forces as well as external support reactions put together, which you cannot determine by equations of statics, we call it as degree of static indeterminacy. Here if you take only the external support reactions, because generally we determine the external support reactions treating the structure as a whole, equilibrium of the total structure as a whole, we treat it and determine that unknown support reactions. So if you cannot determine the support reactions by equations of statics equilibrium, that is only 3 equations are available. If you cannot determine that unknown support reactions, then we say that as degree of external indeterminacy. And this internal indeterminacy is the number of unknown internal member forces which you cannot determine by equations of equilibrium alone. Because here unknowns corresponds to internal force as well as external support reactions. These we determine by equations of only 3 equations of equilibrium, whereas this we determine by considering the equations of equilibrium at all the joints of this structure, here including that support joints. So all put together we consider here for total, but for finding the reactions we consider only 3 equations of equilibrium, and for internal member forces we consider the joint, all the joints of the structure. So we consider the free body diagram of each joint of the structure and apply equations of equilibrium for finding the internal member forces. All the members which are meeting at the joint, there we apply equations of equilibrium. But for finding support reactions, we consider the total structure as a whole and apply equations of equilibrium. That is only 3 equations. So this degree of external indeterminacy is nothing but the total number of external unknown support reactions minus 3 equations of equilibrium, because for planar structures only 3 equations of equilibrium we have, that is sigma Fx0, sigma Fi0 and sigma Mz0. And degree of, this is degree of external indeterminacy. Degree of internal indeterminacy, so you can find out as the difference, degree of internal indeterminacy, you can find out by finding the total degree of indeterminacy minus degree of static external indeterminacy. So thereby you can determine whether all types of indeterminacy in the given structure. So generally we determine only the total indeterminacy of the structure. Further, if you want to know what are the unknown support reactions only, what are unknown internal members force only, then you have to find out degree of external indeterminacy and internal indeterminacy. Remember, the total indeterminacy of the structure is always pertaining to the total indeterminacy with respect to the external reactions and total indeterminacy with respect to internal indeterminacy. So in this particular example, the first set, here we have a continuous beam, here I have an arch, here I have a rigid plane frame, here I have a plane truss, and this is again a rigid frame which we call it as bowstring bridge. Bowstring bridge structure. It is called as bowstring bridge. It is similar to the bowstring profile, bow and a string. So this is again a plane, rigid plane frame structure. For all these, here all are made out of by only one-dimensional members or line members. All these structures A to E, they are made out of only by line elements, and each of the line elements are interconnected by rigid or pin joint. If it is pin joint, we say it is truss. If it is rigid joint, we say it is as a rigid frame. And all are called as frame structures. And here all members lie in only one plane. So that's why it is called as plane frame structures. So all are called plane frame structures, and except these, the rest are all called rigid plane frame structures. Here I have considered one more internal hinge. That's it. Then here also I have considered one internal hinge. Actually, this is only one member. Here also this is one member. Member, how do you define a member? That is, member of a structure is nothing but the distance between the two nodes, two end points of the element. We consider if you have suppose at the two ends, then we call that as a member. Here, this is not a support end point. This is not end point where the transfer of force occurs. So that's why these points we call it as internal hinge. This is called internal hinge. It is not a support or a continuous joint. So here, all these joints, they are called continuous joints. Here, it is not a continuous joint, it is just a hinge in the one member itself. That's another thing you have to remember in the assembly of structures. So whenever you have that type of arrangement in a structure, then you have to slightly modify these particular equations. So here I have to say m plus r minus 2j minus imposed condition, imposed external condition. Here also minus imposed condition. So that imposed condition means if you have an internal hinge, I am just externally imposing a condition that here there cannot be any moment transfer. Otherwise, in the entire structure there will be movement. Because it's a beam flexural member, there will be movement at all the points. But at this point, there was no movement. Speciality is there. That's imposed condition externally. So that is why this imposes a condition in the given structure externally. That's why for finding out the degree of static indeterminacy, we have to use that one more condition which has been imposed externally. That is the modification you have to take. Generally, it will not be present in all the problems, only in special cases. That's why I have taken this for an example. Now we will work out. It's a very simple phenomenon. First you have to identify what type of structure given structure is, and then you have to count the number of nodes or joints, number of members, number of support reactions. That's all we have to count. So here, as I told you already, all are plain, rigid, plain frame structure except this. This is rigid truss, not rigid, plain frame truss. Or plain, it's also called a plain frame structure, but pinned plain frame structure. So we have to use the first formula. In all other cases, I have to use second formula, and in these two cases, since imposed condition is there, that extra term or extra imposed condition I have to take. That's all. That by observing the structure, you have to do all these things and then apply this equation and arrive at the result. So if you take first problem, first I have to find out m. M is nothing but number of members or elements in the given structure, number of line elements in the structure. Here how many members are there? One member. This is also, I told you, only one member. This is an internal hinge. I don't consider this as one member, this as another member. That is not. Because it is not a support, it is only an internal hinge. So there are only two members. So M is equal to 2. Then J equals number of joints or nodes. It's also called as nodes. So number of joints or nodes, 1, 2, 3. They are the joints. This is not a joint, right? The joint is that particular thing where transfer of force is there to the adjoining members. Here, there is no question of any transfer of force occurring. That's only an internal, built-in internal hinge. So only 3 joints are there, so that you have to take it. And or number of support reactions, number of boundary conditions, that is number of support reactions, it's boundary conditions. Here, as I told you yesterday, so we are having 4 types of supports for the plane structure. One is hinge type of support, another roller or simple type of support, another fixed type of supports. Here, there won't be any movement horizontally and vertically. Because of that restriction in the movement, there will be inherent force which we call it as the reaction. And here it is not allowed to move in the vertical direction, so there will be an inherent force which is holding that or which is preventing that vertical motion, and here you have only one vertical reaction, here you have two reactions, here it is not allowed to move at all. So all the three motions are restricted, so to prevent all the three motions there must be three reactions. So totally 2 plus 1, 3 plus another 3, 6. Total number of support reactions are 6. So it is a continuous beam structure. So I have got up that is a rigid plane frame structure. I have to apply this formula, and there is an internal hinge. I have to apply an imposed condition. Therefore, degree of static indeterminacy is equal to 3m plus or minus 3j minus imposed condition. So that is equal to 3 into m, that is 3 into 6, 2, 6 plus r is 6, 3 into j, that is 3 into 3, 9 minus imposed condition, that is always moment at internal hinge is 0, m is equal to 0 is the imposed condition. One imposed condition is there. So therefore, this is 12 minus 9, 3, 3 minus 1, 2. So degree of static indeterminacy is 2. For this particular problem, degree of static indeterminacy is 2. That's what we are going to get. So out of these 2, then degree of external indeterminacy is r minus 3 minus imposed condition. That's the extra condition we have to take. So here r is equal to 6 minus 3 minus 1, so it is 2. So it is, we say this structure is totally indeterminate to the degree 2, and it is externally indeterminate to the degree 2, and degree of internal indeterminacy is I minus e, that is 2 minus 2 is 0. That means it is internally determinate. So this structure, we say it is internally determinate, externally indeterminate to the degree 2, and put together it is altogether it is indeterminate to the degree 2. That is external plus internal. That is what we are doing. Is it clear? This is the first example. Likewise, this we can do it. Here, what is m? This b to take problem b. So m, because it is also a rigid type of plane frame structure. Imposed condition is there because of this internal hinge. I have to apply the formula I is equal to 3m plus r minus 3k minus imposed condition. Imposed condition. So here m is equal to 1 because there is only one member. Of course, it's a curved member. I told you yesterday. So all these type of structures, frame structure made out of by only line elements. So that line either it may be straight or it may be curved in profile. Here it is curved. So only one member with one intermediate. So m is equal to 1, or is the total number of unknown support reactions. Here both are hinge. So 2 reactions here, 2 here, 2 plus 2, 4, and j, number of joints 2. Don't treat this as a joint. Only 2 joints. Hinged joints, that's only internal hinge. So j is equal to 2, and imposed condition is 1. That is because of internal hinge, there will be no moment, and that's imposed condition. Therefore, I is equal to 3m, that is 3 into 1, 3 plus R is 4 minus 3J 6 minus imposed condition is 1. Therefore it is 4, 3 plus 4, 7 minus 6, 1, 1 minus 1, 0. So that means this structure is determinate. It is called a three-hinged arch type of structure. Three-hinged arch is always a determinate structure because I is equal to 0. This is what I told yesterday. The total indeterminacy, if it is 0, we say that structure is determinate. If it is greater than 0, then it is indeterminate. If it is less than 0, it is unstable. This is what I told. So this structure is determinate. Whereas the first one is indeterminate because I is greater than 0. You got I is equal to 2, so which is greater than 0, so it is indeterminate to the degree 2. Here it is a determinate structure, and of course that you can check up the degree of external indeterminacy is equal to R minus 3 minus imposed condition. So R is equal to 4 minus 3 minus imposed condition is 1, that is also 0. And of course internal indeterminacy is I minus E, that is also 0. All indeterminacies are 0. The structure is determinate structure. It is not indeterminate. So that is about this. So first one is over, the second is over. So here, this is another structure that is same similar to the arch, only thing is internal hinge is not there. So here again M is equal to 1, only one member, and J is equal to number of joints, 2 joints, and R equals number of support reactions. Here totally 4 support reactions, and I is equal to 3M plus R minus 3J. No imposed condition, don't use it. Only the formula we have to use. This is 3 plus R is 4 minus 3 into J, 3 into 2, 6. So this is 1. So which is greater than 0, so it is indeterminate. So this structure is indeterminate structure. It is called two-hinged arch. Earlier was three-hinged arch, so it is determinate. This is a two-hinged arch, it is indeterminate. Like that, if you have fixed support here, it is also indeterminate naturally, because we will get R as 6 in that case. So naturally it is also, I is also greater than 0, so it is indeterminate. Only except three-hinged arch in the curved profile, all are indeterminate structure, and degree of indeterminacy is 1. You can check degree of the external indeterminacy is R minus 3, that is 4 minus 3, 1. And degree of internal indeterminacy is I minus E, that is 1 minus 1, 0. So this is internally determinate, externally indeterminate to the degree 1, and totally it is indeterminate to the degree 1. So that means out of 4 external support reactions, 1 external support reactions you cannot determine by equation of statics. So other 3 you can determine. And in the moment you determine support reactions, totally structure becomes determinate, and because internally it is determinate, at any point we can find the internal force without any problem afterwards. So this structure becomes automatically. So that is about this second example. So next, if you can see this rigid plane frame structure, so you can count. There are no imposed condition, so you can use the formula for finding the total indeterminacy as 3m plus r minus 3j, the second formula, and you have to find number of members or elements. You have to count it here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. M is equal to 14. 14 elements are there and total number of joints here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Totally 12 joints are there and total support reactions. Here it's a fixed support, 3 reactions. This is also fixed, 3 reactions. Hinge, 2 reactions. Roller, 1. So totally 3 plus 3, 6 to 8 plus 1, 9. Or is 9 number of support reactions. So therefore, degree of static indeterminacy is 3m, 3 into 4, that is 42. Then plus r is 9 minus 3 into j, 3 into 12, 36. This is 51 minus 36. So that is 15. Degree of static indeterminacy of this is 15. You see the magnitude. It goes on increasing as the number of days it increases. If it is only single, okay, only 1, 2, 3. If it goes on increasing, multi-story, multi-base structure, degree of indeterminacy also goes on increasing. Likewise, kinematic indeterminacy also goes on increasing. We have to resort to computer for finding the analysis. So it becomes very difficult for hand. So this is the degree of total indeterminacy. Degree of external indeterminacy is r minus 3. And so that will not alter. For finding the external support reaction, only we consider structure as a whole. We consider 3 equations of statics. Sum of horizontal forces 0, sum of vertical forces 0, and sum of moment about any one of these points, joints, is equal to 0. That's all, 3 equations. And total support reactions. We consider total structure as a whole, equilibrium of structure as a whole for finding this degree of external indeterminacy. For finding internal indeterminacy, we consider each joint. For member, we consider free body diagram. Either you take a section, consider free body diagram towards either left or right, and consider only those cut members, internal force and support reactions, and find the degree of indeterminacy. So this is r minus 3, that is 9 minus 3, 6, and degree of internal indeterminacy is I minus e, that is 15 minus 6, 9. So this structure is externally indeterminate to the degree 6 and internally indeterminate to the degree 9. So and totally external and internal put together, it is indeterminate to the degree 15. That's all. That's very simple. You have to remember the formula, right? So that means this structure either support reaction also you cannot determine fully by equations of equilibrium alone, or internal member forces also you cannot determine by equations of equilibrium at all the joints or by considering free body diagrams. So that is about this problem. Next, this is a plane truss. It's a plane truss because all members lie in one plane and all are line elements. It is made out of line elements and all elements are interconnected by thin joint, so no movement. So we have to use the first formula here. Degree of static indeterminacy is m plus or minus 2j, no imposed conditions. So here m, number of members 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 members. Joints 1, 2, 3, 4, 5, 6, 7. Joints 7. You can number joints also we can number, members also. This is what we do by solving the problem. First we determine the number of nodes, determine number of members, like this. So naturally you have to do that exercise first. 11 members. Then you have 7 joints, then or number of support reactions. So you have support for this structure, only 2 supports, one is hinge support and a roller support. Hinge support you have 2 reactions, roller support you have only 1 reaction. So it is 2 plus 1, 3. Therefore, degree of static indeterminacy is m plus or minus 2j, that I have already written. So m is 11, r is 3, minus 2j, 2 into 7, it is 14, it is 0. That means this structure, though it looks big, it is a determinate structure. You can just apply the equation of statics and do the analysis. This sort of problem I have already done. So support reactions also you can determine by equation of statics, and all internal member forces also you can determine by considering equilibrium of all the joints. Each joint separately you can consider, apply equation of equilibrium. Draw the free body diagram of all the members meeting at all the joints, apply that equations of equilibrium, you will get the member forces. All the member forces, support reaction, you can determine by just equation of statics alone. So this is a determinate structure. Right? Though it looks big, it is basically a determinate simple structure. So, and of course, naturally external indeterminacy also has to be 0, internal indeterminacy also has to be 0. E equals r minus 3, that is r is 3, e minus 3, 0. Internal indeterminacy is I minus 3, that is 0. So this structure is determinate. So this is over. Then lastly, I have taken this rigid plane frame structure because all members here, all elements lie in one plane, so planar structure, and all joints are rigid joint, all elements are rigidly connected, so all elements lie in one plane, all are line element, so it is a rigid plane frame structure. Rigid plane frame structure. So each terminology. So it's a rigid plane frame structure. Degree of static indeterminacy is again 3m plus r minus 3k. No imposed conditions, forget it. M is number of members. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Number of members are 14. Number of joints 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Totally number of joints 10. So add all number of support reactions. It consists of 2 supports, both are hinge type of supports, 2 reactions, 2 here, 2 there, so all will be 4. Therefore, degree of static indeterminacy 3 into m, 3 into 14, 42 plus r is 4, 3 into j, 3 into 10, 30, that is 46 minus 30, it is 16. This structure is indeterminate to the degree 16. 16 unknown forces, 16 internal member forces as well as external support reactions you cannot determine by equation of statics. So degree of external indeterminacy r minus 3, that is 4 minus 3, 1. So 3, 1 support reactions you cannot determine. Here there are 4 support reactions. Out of that 4, only one you cannot determine, remaining three you can determine. Naturally, three equations are there, so three reactions can be determined, one you cannot determine because there is no equations available. For when you consider structure as a whole, equilibrium or structure as a whole, you can have only three equations. So we have four unknowns. Naturally, degree of the external indeterminacy is 1. So degree of internal indeterminacy, internal member forces. Each member has three internal forces: axial, shear, and moment. Each member. There are 14 members. 14 into 3, 52 unknown member forces are there. And by considering equilibrium of all the joints, you cannot determine all the internal member forces, and that internal member forces indeterminacy is this total indeterminacy minus external indeterminacy is 15. So 15 internal member forces you cannot determine by equations of statics. So this is how you can evaluate degree of static indeterminacy as well as what is whether it is determinate or stable. Of course, here I didn't set any problem which gives you a less than 0, a negative value. If you are getting, then you have to say that structure is unstable. There is no analysis for unstable structure. You should not start your analysis process for unstable structures. So that is about this complete degree of static indeterminacy. I hope I made the thing, whatever I have told yesterday, clear by way of the examples. Because as per syllabus, you have only the plane frame rigid structure as well as plane pin jointed structures only that is being said. So I have taken some few examples for finding the degree of static indeterminacy. Next, we will take up the kinematic indeterminacy. It is the number of unknown joint displacements. Because as I was telling, so analysis involves or analysis consists of determining support reactions, internal member forces, along with the displacements at various joints. Forces as well as displacements we have to determine on account of the external loading in the structure. So forces we saw, now we talk about displacements. So at each joint in all planar structures we have three displacements, that is horizontal displacement, vertical displacement and a rotation. But if it is pin jointed, rotation will automatically be there, right? It is allowed, and other two also possible there. Only supports, if it is fixed support, no displacement at all. At that point, only hinge supports, you have only rotation occurring, two translations will not be there. In roller, only rotation will be there, as well as one translation where roller is there, in which direction it can roll. There, that displacement will be there. That you can. Whereas other displacement, vertical direction, there won't be any motion. So now we will take up this example. So here, this example, as I told you, there will be three displacements in general for rigid frame structure, and if there are j number of joints, 3 into j is the number of unknown forces, and at support reactions there won't be any displacement, you have to subtract. So this 3j minus or we call it as the kinematic indeterminacy. So at each joint there will be three displacements. If there are j number of joints means 3 into j displacements, and at support reactions there won't be any displacement because the displacement is held by that force or reaction. So naturally 3j minus r will be the only known displacements in the entire structure. So this is for rigid frames. Rigid frames. And for trusses, you have only 2 displacements and 2j minus 4 for trusses. So moment we don't consider at all because each joint is thin joint. Now we will remember the 2 formula. As we remember for finding static indeterminacy, the 2 formula of kinematic indeterminacy, this is the formula. It is also called as degrees of freedom. That is freedom for motion or movement, whatever the freedom. So there will be 3 types of motion because the movement can occur in any direction. But for analysis purpose, always that any direction movement is resolved into 3 orthogonal directions. So 3 orthogonal directions when we resolve. So in planar structures we get 3, whereas in general structures, general space structures, we have 6 degrees of freedom. That is, say, 3 translations along 3 axes and 3 rotations. Out of that, say, 6, 3 are absent in the case of planar structures because those displacements, 3 displacements would be out of plane. Out of plane means structure has to go out of the plane. That means it is unstable. We are not considering that unstable structure. So we restrict the movements in planar structures to only 3. So here we have to count number of joints and number of support reactions. So in this F problem, since we have to find kinematic indeterminacy, degree of kinematic indeterminacy, count the number of joints. How many joints are there? 1, 2, 3, 4, 5, 6. 6 joints. So, or number of reactions. So, here 2, here 2, here 3. So, 4 plus 3, 7. 7 reactions. So, therefore, kinematic indeterminacy in general it is 3 into 6 minus 7, that is 11. Degree of kinematic indeterminacy of this problem is 11. So you can sketch, if you want, I will show the sketch of displacements where they are occurring at all the joints. I will mark it and show you. So this is the structure I am considering. First I will observe the supports. Here I cannot have any displacement because generally at each joint you have 3 types of displacement. One is horizontal, another vertical, another rotation about an axis normal to the plane. 3 displacements are possible. Here all these 3 displacements are 0. Here this is 0, 0, 0. Because it is fixed here. Here, this is 0. Horizontally it cannot move. Vertically it cannot move. But rotation, it will be there at that joint. 1. Here, same thing as this. Vertical, it is 0. Horizontal, 0. And this rotation, it is there. 1, 2. Next you come to the joint. Here all 3 are possible. So this is there, this is there, this is there. So 3, 4, 5. Here again all 3 are there. 6, 7, 8. Here also all 3 are possible. That is 9 and 11. I have determined here total degree of kinematic indeterminacy. I have shown at each joint what are the displacement. Here horizontally it can move, vertically it can move, it can rotate also. Here also all 3. Here also all 3. Here nothing is possible. Here only rotation is possible. here rotation is done. I have marked all the no displacements. Right? So, if there is one condition here, they may say members are axially rigid. So, sometimes, because in slope deflection in undergraduate level, it has the one basic assumption they are doing is all members we assume them to be axially rigid. That means it cannot undergo deformation on its own within that. Any point, there is no contraction or elongation of the member. There is only a rigid body motion is possible. Whatever the length which is there originally, same length will be there even after displacement. Bodily, the body member or element moves. Rigid body motion it is called. Bodily it moves. There is no contraction or elongation of the member, but the bodily it moves. So if one node, left node moves, right node also moves by same amount. There is no difference. If there is difference in the motion between left hand and right hand, that means this member has undergone elongation or contraction, which is not possible. It is axially rigid. There is no axially rigid means there is no axial compression or tension of the member. So, if we assume the members to be axially rigid here, then the kinematic indeterminacy reduces. Suppose if we say here it is axially rigid. So, if all members, all elements are axially rigid or assumed to be axially rigid. That means no member undergoes axial compression or elongation. If at all it moves due to load, simply it moves. This joint, whatever movement it is there here, so this joint also will move by same amount and this also will move by same amount. Bodily it moves. There won't be any elongation or compression of that member, all three members. They move by same amount. Likewise, this if it moves, this also should move by same amount. Right? Whereas this cannot move. So therefore, this motion is ruled out. So you have to examine that. Whenever we say this condition, that is all members are axially rigid, so forget about support. Support, it remains same. There will be only two support reactions. Here you consider which are possible. Now, here, if this end moves like this, already marked by same amount, then this also should move by same amount. Because we say axially rigid. That means whatever this end moves, right end also should of this member should also move by same amount. That means this 3 and 6, they are not different. They are same. So this 6, I have to call it as 3 only. Similarly, this 9 also, I have to call 3 only. Because there is no contraction or elongation. If it is axially rigid, that means this, whatever motion is there, that is there of course. Other 2 horizontal motions, they will be same. It cannot be different. The moment you assume axially rigid. So all I have to call it as 3, 3, 3 only. They are moving by same amount. There won't be any difference between left hand and right hand movements. The rigid body motion will be there. That is what you have importance to remember. Rigid body motion. That means there won't be any contraction or elongation within the body. Body moves rigid as it is, but its length will not alter. Its area of cross section also will not alter. Contraction or elongation will not be there. Bodily it moves and it will not change in its dimensions. It will be there as it is, even after motion. That's the thing. Likewise, here, this motion, 4, 7, 10, we examine. Suppose if this moves in this vertical member, this end moves up, this also should move. But here it is not possible. You have a hinged support. Correct? This I made it as 0. So this also 4, I have to make it 0. Here, this is a very, very important thing. Already you must have studied in undergraduate level. Sway, non-sway. This is called sway. Sway always we define as the translatory motion normal to the axis of the member. For all the vertical members, axis will be vertical. Normal to the axis is movement in the horizontal direction. That is the delta sway. For all the horizontal members, sway is in the vertical direction. Sway we define as the translatory motion normal to the axis of the member. This motion. So B, there won't be any motion. Here, likewise, 7. If this moves, this also should move, but it is 0. So this also has to be 0. On same argument, 10 also has to be 0. There won't be any motion, translatory motion. That means beams are not undergoing any sway. Only columns are undergoing sway. This is you have done in your undergraduate level. This is a very basic, important thing because in stiffness method, we talk about only unknown kinematic independency, unknown displacements at all the joints. So you have to correctly identify what are the unknown displacements which are possible at each joint. So now you see the moment you assume all members to be axially rigid, the number of unknowns, of course rotation, it will be there. So 3, this will be 4, this will be 5, this will be 6. Kinematic independency will be 6. See, from 11 it has come down to 6. The moment we say numbers will be axially rigid. So then kinematic independency will be 6. Here, this is another thing which you have to remember. If you give me the problem, assuming members to be axially rigid, find the kinematic independency. Then you have to do this sketch. First, you want all possible displacements and then go on numbering which are the displacements possible. 0, 0, 0 here, because possible displacements are 3 at each joint. So here no displacements possible, here only 1, here only 1, 2. Then here, this is not possible, this is possible, 3 I am calling, so this is 4. Here, this is not possible, this will be 3 only, so 5, that is possible. Like that, you have to mark and identify the kinematic independency. Important concept in stiffness method of analysis. You have to identify what is the structure, what is the indeterminacy, what is static indeterminacy, as well as kinematic indeterminacy. So this is about this problem. Then if you take next G problem, so on similar lines, the moment you did this F, G also on similar lines. Here, this is the frame we are having. So this is the frame. So if it is not axially rigid, so it is just as it is general frame. As usual, see it is simple. You have to count number of joints. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Totally number of joints are 12. 3, 6, 9, 12. This also you count. Supports also you count as a joint. J equals 12. And since it is a planar structure, 3 possible displacements. So kinematic independency is 3 into J minus or number of support reactions. And so here you have 3 support reactions fixed end. Here you have fixed end 3. Here each 2 reactions. So 3, 3, 6, 2, 8. R is equal to 8. So this is 12 into 3, 36 minus 8. So this will be 28. Kinematic indeterminacy is 28. So which are the one? As usual, you mark it. So at each joint, you will have 3 possible displacements. One translation along x direction, another translation along vertical direction, another rotation possible. You mark all those at each joint like this. You mark it. So I have marked 3 possible things. Which are possible, you write it. So this is hinge. So horizontal is not possible. Vertical is not possible. Rotation is possible. 1. Here, fixed end, all 3 are not possible. Here, all 3 are not possible. Okay? Next, here. All 3 are possible because it's a continuous joint. So 1, so this is 2, 3, 4. Here 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So kinematic indeterminacy is 28. You have to use the formula and you have arrived at kinematic indeterminacy. And in this structure, at each joint I have marked what are the possible displacements you are determining. Now, suppose if it is axially rigid, case comes. So axially rigid, here no problem, it remains same. Here, axially rigid means whatever this end moves, this also same amount, that also same amount. Both these elements has to move by rigid body by same amounts. So that means these 2 becomes 2, this also becomes 2. They are not different. Then vertical, there is no, this number if you take, if this moves, this also should move, which is not possible because at base it is held here. So all columns, one above the other, they cannot move. So that means all these, I can make it 0. Likewise, all these, I can make it 0. This also is not there. All these I can make it 0. And horizontal, they are same. Here also horizontal 2 is, because the verticals are all 0. So this is 2 I am calling. This is 3. This is also 3. This is also 3. Then this will be 4, this will be 4, this will be 4. Okay? Same motions, not different. Then rotations, 4 is over. So here already I have marked, here this will be 5, this will be 6, this will be 7, this will be 8, this will be 9, this is 10, then 11, then 12, then 13. So these numbers are axially rigid, then kinematic indeterminacy is 13. See, drastically it has reduced from 28 to 13. So you can mark it what? See these particular columns, they move like that. horizontal motion. So all these portions, 2, 2, 2, this is 3, 3, 3, this is 4, 4, 4. Horizontal motion. Vertical motion is not at all there, forget it. Then rotations. Rotation here I have taken as 1 rotation is there, then 4 is over, here rotation is there, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's what. Okay. That I have marked separately. If members are axial. So that is about this. How to find the kind. Very, very important thing. Because all your stiffness method, this is what we have to do. Kind of flexibility method, static indeterminacy. Unknowns. If you know what is that, you have to determine during the analysis. Then you proceed. Generating flexibility and stiffness matrix. Then relationship between both and displacement. Analysis will be complete. It is as simple as that. So then if you take this, third one, so it is a plane truss. Here you have to be careful. Possible displacements, because each joint is pin joint. It is not rigid joint. Pin joint, so movement will not be there. So at each joint you have only 2 displacements possible. 2 translations. No rotation. Here on. At all the joints, you have only 2 translations. No rotation. In rigid plane frames, rotation also does come. Now in this truss, so number of joints 1, 2, 3, 4, 5, 6, 7, 8. Here is equal to 8. Support reaction. Here 2, here 2. 4. All is equal to 4. Therefore, kinematic indeterminacy is 2 only, not 3J. 2J, because at each joint you have only 2 displacements. 2J minus R. It is as simple as that. At each joint you have 2J. At number of support reactions there cannot be any displacement. So that is minus R. That is the total unknown displacement to be determined during the analysis. So here this is 2 into 8, 16 minus 4. It is 12. So kinematic indeterminacy is 12. Which are those 12? Here 2, 6. Here 6, 12. Here there is no question of any members to be axially rigid and other. So 12 unknown displacements are there repeated. Don't bother about axially rigid. Axially rigid you can consider only in rigid frame structures, that is in beams and rigid beams. Trusses only 2 displacements, horizontal or vertical. This over. Next, from complicated to simple structures I am coming to. So here is a continuous beam. In beam, generally what we do is we assume beam to be axially rigid. But generally, since I have given only, we are treating it as rigid frame structure, I am taking 3. Right? If they say axially rigid, play that reduction. That's it. Here also, how many joints are there? 1, 2, 3, 4. J is equal to 4. At each joint, strictly speaking, there will be 3, similar to rigid plane frame. 3 displacements possible. Right? So, kinematic indeterminacy is 3J minus R. R is here 3 reactions, here 1 4, 1 5, 3, 8. R is 8. So kinematic independence is 3 into 4, 12, minus 8, 4. So you mark which are the 4 unknown displacements. So here fixed support, no displacement, 0, 0, 0. This is fixed support, no displacement. This is roller support, only displacement is there in the roller direction. There won't be any displacement here, right? There won't be any displacement from rotation. And rotation is possible. Rotation is possible. One here also, rotation possible. Horizontal, I will go like this. Horizontal displacement possible, rotation possible, vertical not possible. Here also rotation possible, translation possible, vertical displacement is not there. Right? Here no displacement, here no displacement, here horizontal displacement is there because roller. And rotation is there. Okay. Roller end it can rotate. So rotation is there. Here, since it's also roller, horizontal is there, rotation is there. So 1, 2, 3, 4. Here 0, 0. 4. 4 displacements. If it is axially rigid, then whatever this motion is there, this also should move by same amount. There is no separate 3. That's also. Right? So then 1, 1, this is 2, this should be 3. If this one, now you observe, if this one is there, this also should be there, which is 0. So naturally, this is the 0. Here, there cannot be any displacement. Because one left hand, if it moves, right also to move by a one. Then, if you go on moving, this rigid body motion, this also should move, this cannot move. Likewise, this also cannot move. So this is not there at all. So only 2. If it is axially rigid, it is only 2. Kinematic independence is 2. That's only rotation at those points. No translation at all. That means no sway. All beams are non-sway that you have already considered. You have told all beams are non-sway because of this. No translation motion. If at all there is translation motion, then we call it as sway, not non-sway. Otherwise, no sway. It is non-sway. All beams are non-sway. But rigid frames, they can be swayed. But there, as long as it is truly vertical, not inclined, truly vertical, that is rectangle or orthogonal frame. If it is orthogonal frame, vertical translation is not there, that means beams are not undergoing sway, only columns will undergo sway. Only rotate. At each story level, the same sway will be there. First story, one sway, second story, another, third, another. Only story. So that point it should be very well remembered because they are used in earthquake analysis also at each story level. Only column members not being like that. So this is done. Then of course these two are very simple problems. So here kinematic independency at all these points it is 0. Here 0. Here Yes, horizontal is there. Here, horizontal is there. Both. Of course, first, I will take it is not undergoing, all members to be axially. So that means this also has to be 1, this also has to be 1, because they should move by same amount. Vertically, it is not possible, because if this moves, this also should move, this also should move, which is not possible here. So this is pulled out. Right? Only one square and rotation. It is there, rotation it is there, 2, 3. So kinematic indeterminacy is 3 for axially rigid case. This is what you have done. Maximum kinematic indeterminacy not greater than 3. 3 is the one you have analyzed this problem in your undergraduate level. But if it is, the assumption is not there, then kinematic indeterminacy will be 3k minus, or number of joints, 4 joints, that is 3 into 4, or number of support reaction, 3 here, 3 here, 6, so 12 minus 6, it is 6. Kinematic indeterminacy is 6. If it is accelerated, it is only 3. That is very simple, which you have done. So this is over. Then coming to this, it is called as cantilever truss, right? Because this is fully support, so this you can treat it like this. 4 single supports. You can take it so you can treat this problem like this, either like this or like that. There is no member here. It's fully support, meeting support. Now you see. So, because it is a truss, each joint is pin joint. It's a truss. So possible 2 displacements. Here all are hinge supports, no displacements. All are 0. Only this point. Kinematic indeterminacy is, as I told you, in truss we don't bother about accelerated case. So here, kinematic indeterminacy is horizontal. So I hope I made this indeterminacy for all the problems, which is the basic idea that so one should be well versed with this. There should not be any ambiguity in your mind how to find degree of kinematic indeterminacy or static indeterminacy. Then about 5 minutes I will spend on equilibrium and compatibility conditions. So I have explained yesterday fully what is equilibrium condition. Here also I was repeatedly telling equilibrium condition and all. So equilibrium condition, to be specific through an example, equilibrium and compatibility conditions. So I will just consider a frame and consider this joint. So consider a joint 1 of a rigid plane frame. So here a joint 1 of the rigid plane frame. There are 2 members, 1 and 2. This is one member, second member. This is first member. Suppose there is a external load Wx, Wy, and of course, here let there be a moment also in Z at the joint 1. So consider a joint 1 of the rigid plane frame wherein external load Wx, Wy, and Mz are acting. Then the equilibrium condition at joint 1 requires, I have defined yesterday what the equilibrium condition is. Equilibrium condition is applied at all the joints of the structure, and it requires that algebraic sum of all external load should be equal to the algebraic sum of all the member end forces. Member end forces means resolved member end forces along 3 fundamental directions. That's what it means. Then the equilibrium condition here, it requires sigma fx is equal to 0. It requires is sigma fy equal to 0 and sigma mz is equal to 0. Joint 1 requires this condition, equilibrium condition. So that means here the external load in x direction is Wx, the external load in y direction is, I will take the positive directions of this x, y, z like this. All forces along x direction from left to right positive, all forces from bottom to top positive, and all rotations clockwise positive, all moment clockwise positive. That is the sign convention and adopt. Here external Wx, it is in the positive direction of x, so this is positive. This will be negative because it is opposite to y direction, that is negative. So this is clockwise direction, so it is positive external. Then coming to the member and forces. So in the member 1, it is a rigid plane frame member, there will be 3 internal forces, 1 horizontal, vertical, and moment. So this is Fx of one member, Fy of one member, this is Mz of one member at the joint 1. If you draw the free body diagram of the member 1, that is how, because I told you in the beginning that each member end at any point of element or member of the rigid plane frame, there will be 3 forces. One is axial force, another shear, another bending moment. Likewise, at the same joint 1, I have another member, that is member 2, meeting at the joint 1, and here this member at the joint 1, you should have an axial force as the internal force. This has Fy2, this has Mz. So here the equilibrium condition demands or requires so algebraic sum of all internal forces and all external forces at the joint which is being considered should be 0. So that means sigma fx 0 means this fx of first element, it is in the positive direction only have taken to start with. If it is opposite, you take opposite. After analysis, supposing this happens to be negative, or if it is 0, take it as 0, that's all. fx1, then fx2, then plus wx is equal to 0. This is the first equilibrium condition at joint 1. Then fy1, fy2, these are the internal forces which I have marked. All the internal forces of all the members meeting at that joint, internal member forces, plus external support reaction. This is minus Wi is equal to 0. That is sigma Fi 0. Sigma moment 0, 3 equations. So that is mz1, mz2 is equal to minus plus mz equals 0. This is what I defined as equilibrium conditions are applied at each joints of the structure. So equilibrium condition demands or requires algebraic sum of all internal member forces meeting at the joint along with the external loading should keep the joint in equilibrium. That is sigma fx, sigma fy, sigma mz should be 0 at the joint 1. So this is the equation. This is exactly what I meant. This I have explained with respect to a general rigid plane in joint. Likewise, we can consider a general joint of a truss. At that point also, in truss you have only one axial force, no shear, no moment. So you can just take the algebraic sum and say that is what it applies at each joint. That's why we are determining the degree of static indeterminacy. I consider 3 forces each, like this. Right? In trusses only 2 you have to consider moment, and that's it. Likewise, if you say compatibility condition, which I explained yesterday, to a specific problem, compatibility condition means, suppose if you take a same rigid plane frame or a truss or a beam, whatever it is, suppose if I consider a joint 1 here, after analysis, at the joint 1, if suppose you have a displacement u, vertical displacement v, and a rotation theta, because we are talking about compatibility forces, here displacements. So the compatibility condition at compatibility condition at joint 1 requires that the displacements at 1 at joint 1 displacements at the ends of all members meeting at joint 1 should displacement at the ends of all members meeting at joint 1 should have same displacements as that of joint 1. The member ends of all member ends which are meeting at the joint should also have same displacement. That means if you take this as member 1, this as member 2, these are the 2 members meeting at the joint 1, the 2 members meeting at the joint 1. This member, since it is vertical member, you should have same vertical displacement. V should have same horizontal displacement u, we should have same rotation theta at this joint 1. Similarly, this member 1. Similarly, this member 2 at here, member 2 at this joint 1 should have same horizontal displacement u, same vertical displacement v, and same rotation theta. This is exactly what is compatibility condition. That is the first component of the displacement along x, y, z direction of all the member ends meeting at that joint should be same, and that is equal to joint displacement. That is how I defined yesterday the compatibility condition. Compatibility condition demands that any joint, the displacements of all the members at that meeting at that end should have same displacement components which is equal to the external. So this is what I have told you today. Equilibrium condition, compatibility condition, boundary conditions, support conditions I have used, indeterminacies I have used with respect to example I have explained here, and then that equivalent joint loads, all loads for analysis purpose, we have to take it as acting only at the joints of the structure. Even if it is acting at the members, we have to find equivalent load at the joints. As if they are acting at the joints only, we have to consider that, as well as if you have number of loads like gravity load, temperature load, or settlement of support load, then you can just club them action by that is allowed. That is called principle of superposition. Principle of superposition is valid to consider the effect of all. That another condition that I will explain in detail when we take up an example. That is principle of superposition and how to consider the loads. All loads we have to consider when they are acting at the joint. If at all they are acting on the members, we have to find their equivalent value, and how to find their equivalent value, I will explain for an example. And if at all number of loads are there, as I told you, temperature load, settlement, gravity load, how to consider the effect by using principle of superposition. That I will explain. With that unit 1 may be completed, except that solution of simultaneous equation.